All right, class will come to order. I'm glad you're talking though. This has been such a quiet year. I taught middle school for 10 years, so I was used to just craziness. And then I got to high school, and the students were quiet, and it was weird. But this year has been really weird. It's been a long time since I taught middle school, so I've gotten over it. But still strange to have everybody super quiet all the time. In middle school, it was like you had to rein in the horses all the time. I was always putting the brakes on. High school, I kind of got to prod people and get them to move and make noise. So I was thinking of setting this up in the classroom. It's not a very exciting thing to do. I ended up doing something like this at home last night, so I'll show you my results, but I just found this picture showing a typical earth science experiment to demonstrate what's called specific heat, and sort of. It's more complicated than that. So if you look at the picture over here, there are a couple of equal lamps with equal bulbs, and they're the same distance apart from these two different trays or boxes, and apparently they're geo boxes. And one has water in it, the other has looks like an equal volume of sand. Not necessarily an equal mass. Which one do you think would have more mass? The sand in the box or the water in the box? Sand. Sand is more dense. Sand sinks in water, so it's more dense. So there's more stuff in the same space. All right. So I don't know. That's kind of an important factor here. So if they're the same temperature to begin with, and then you leave them under these lights for a while and you keep recording the temperature, first question is which one's going to heat up the fastest? And second, when you turn off the lights, if you record the temperatures again, which one's going to cool down the fastest? So, any guesses? Raise your hand if you think water is going to heat up faster than sand. 3. And how about the cooling down? Raise your hand if you think water is also going to cool down faster than sand. 2. All right. And Sully and Tommy, I didn't hear your hands pop into existence, so I don't know what you were thinking. So let me show you the results from last night. And I've got a table that I might use up here. These are pictures that I took in our kitchen. And they're a little unclear, but this was, so I put everything in the oven. Oh, I don't know how to pause this slideshow. I don't want to go forward. I put everything in the oven and just left it in there for I don't know how long, but an equal amount of time. How do you pause the slideshow? With spacebar? Maybe. All right. I think this is. I don't even know where I am now. I think this is the beginning. So I put everything in the oven, left it in there a long time, and this is the best thermometer I had at home. And I measured the temperature of the water, and it was 151.9 degrees. So I'm going to put that on my table here. Just after being in the oven, 152 degrees, I'll call it, rounding. And I measured the temperature of the sand, and this was, so I had two different containers of sand. I had one, this one had the same volume of sand that I had water. So the water container was full, this was full, and this was about 162 degrees just after I got it out of the oven. So it seemed like it heated up a little bit more than the water, but I don't really know what the temperatures were to begin with. Could have been that the water was colder than the sand to begin with. I actually think it was the other way around because the sand had been outside, although the water's underground. And then there was this one where I thought it would be good to compare. I took the mass of the water. This was 1.32 kilograms of water, and the glass plus the water was 1.32 kilograms. So I added sand to this until I had 1.32 kilograms in there too. So I had a comparison of equal volumes of water and sand to equal masses of water and sand. And this one looks like it started out at 159.6, so about 160. And then I took all of them to a different part of the house, and I set them here. This was sort of the corner where the kids practiced their violin. And they were all sitting there. I turned the lights off, so it wasn't like this one was in the shade and those were in the light. That was just so I could take a picture. And these were the results. So the one with the smallest amount of sand, it was 104 degrees. And I've got inside and outside measures. When I did this, I wish I'd done it in the beginning. I realized that if I stuck the probe right in the center of the sand, it would give me a different temperature than the outside. After this hot sand has been sitting there for an hour, where do you think it's hottest? On the outside or in the middle? In the middle. So it gives off heat from the outside, loses heat there, and then retains a little bit more in the center. So this would be the hottest part. This was 104. And the full sand, that was 111 on the inside. And now for the water, it was 115. And even more striking, when I went back and I put the temperature probe close to the outside of each container, which one do you think had the most similar measurements between the center and the outside? Like when I go to this with water, do you think for water that's going to be a lot cooler on the outside or just a little cooler? And how does that difference between outside and inside compare to the sand? So again, to clarify my question, which one of these is going to have the biggest difference between the outside temperature and the inside? Sand or water? Sand, you're right. So this is the outside of the full sand, 95.5 degrees. I'll call it 96 degrees. So almost 20 degrees difference between the outside and the inside. And then this the water, 114.6. Oops, sorry, I put that in the wrong place. This should have been 96 degrees, so what would it have been? 15 degrees difference. But this was 114.6, so if I round, it's really same temperature, whether I measure in the center or whether I measure on the edge. And then for the one with not much in it, 87 degrees. So Elijah, you were right on that. I'm going to mute this for a second, which means people from home can't talk. Oh, you know what? Whoever's watching this video, they're going to have no idea what I'm talking about. And that may be a lot of people today. Waiting to get my camera going. All right. So this is what I've been doing and talking about. And all of you've been seeing is pictures, but I've been writing over the top of them. So here are my three different experimental groups. My full quart jar of water, my full quart jar of sand, and then my quart jar of sand that's not full but has the same mass as the water. Because I wanted to compare equal masses and equal volumes. So when I put them in the oven and left them in there for a while, the water didn't heat up quite as much as the other two. And I do think that's an indication that water heats up more slowly. Because this sand I just bought at Ace and they had it outside, so it was around freezing. And the water that I poured into that container would have just come from our pipes, which are in our basement, which are probably in the 50s. So if anything, the water was warmer to begin with, but it didn't reach as high a temperature. Hey, Jace. And then when I took them all out and set them on the table, after an hour, the water had changed from 152 down to 115. So I guess it would be nice to do some math here. If this were So 152 minus 115. If this were 120, that would be 30, and then that's 5 more. So this is a change of 35 degrees. Is my math right on that? Yeah. Wait. No. 30. 37 degrees. Thank you. Bad math. Okay, so that went down 37 degrees. This one went down 51 degrees. Check my math on that. This one went down, so 56 degrees. Anyway, which one heated up the fastest or slowest is kind of unclear. Probably the water heated up the slowest, and definitely the water cooled down the slowest. And then the other cool thing or interesting thing is if you compare the inside and outside, the water temperatures are about the same. And why is that? Why is the water the same in the center and the edge, but the sand is warmer in the center and cooler on the edge? Somehow the heat's getting from the center of the water to the edges and kind of mixing around. Why would it do that better than sand? I think you know, Jace. It's a liquid. It can flow around. The molecules aren't stuck in place like in a solid. So anyway, the point of all this we'll really get to either tomorrow or the next day. Let me unmute this and go to here. And I think, so this, just to give you a preview of tomorrow's warm-up, this is about monsoons. So monsoons are winds, but you also hear, when you hear the word monsoon, if you've heard it, it's probably related to rain. They have a lot of rain. There's some famous monsoon rains in India where they just get tons and tons and tons of rain, and then they have a dry season. But the reason this happens is because the high and low pressures that cause these winds switch. And the reason the high and low pressures switch is because Asia is land. And then there's the Indian Ocean, which is water. And in April through September, when that would be spring through fall, the land is heating up, the ocean's heating up. Which one heats up faster, water or sand? Based on what I was just showing you here, which one changes temperature the most? Here's the water, sand. The sand does. So continents change temperature a lot faster than oceans do. Not only that, but the ocean, even if you heat up the surface of it, the bottom, the cool stuff, is going to come up and mix in, so that slows down the changing. But in summer, the land becomes really hot, the ocean becomes really cool, and you get, I guess I can draw this on here and people will see it. You get convection currents from this. Here's the land. Oh. Here's the land. Here's the ocean. So in the summer, this gets super hot. It heats up a lot faster. This is warm. I think I've done this before, but it's cooler. So the air here is heavier. It's sinking air over the ocean, and you get rising air over the land. This is high pressure. This is low pressure. And you get winds coming like this. So you get this basically a coastal wet kind of climate at this time of year. But then in the winter, when everything starts to cool down, what's going to cool down the fastest? The water or the land? Water or sand? Which one changes temperature fastest? Sand. So this is going to get really cold, and this is only going to be cool. So relatively speaking, this is warmer and this is colder. So you're going to have a bunch of heavy sinking air here, and that's going to move over here, and it's going to rise over there. So you get winds going the other way. So instead of wind coming in off the ocean from toward India, you get wind blowing out toward the sea. So this property of water, where water changes temperature slowly, either when it's heating up or cooling off, is called specific heat. And lots of different types of materials, well, all materials have specific heats. Specific heat table. I'll just show you. I'm almost certain I can get one up here quickly that'll have water on it. Oh, come on. Sapphire, oh no. Specific heat of water. Specific heat. Ah, here we go. Does this have water in it? Yes. Oh, that's a nice one. If I just go to this website and get a good look at it. I guess I should have found myself a specific heat graph earlier. This is, alright, this isn't bad. So don't worry about the units. The units are kind of complicated, but right here, this column, this is one way to express specific heat, and this is another. And if you see water at the bottom, it has very high heat capacity. And what that means is it takes more energy gain or energy loss to change the temperature of water than it does anything else on here. So if you want to heat some water up by 1 degree, you have to keep the light shining on it more than you would have to shine it on anything else to raise it 1 degree. So all this other stuff, these are a bunch of different metals and solids, but if we had one here that would just kind of mix together everything that the land is made of on the earth, it would have a much lower specific heat. So when the sun shines on the land, heats up fast, and when the sun goes away, the land cools off fast, but water, because it has a higher specific heat, takes more energy to change its temperature. Hope you kind of understood what I was talking about there. So the project, just want to show you what's been turned in over the last 24 hours. This is the climate map project. 0 turned in, 18 assigned. So today I would like everybody to turn in your project. It doesn't mean it's done. I just want you to turn it in. Find your slideshow that you're working on. Hopefully you've opened up that template and you've made a copy and you're trying to get going on it. Whatever you have, turn it in here. That way I can take a look at what's going on and see how your progress is going. So does anybody have any questions about what to do on this project? All right, well, later on during class, so if either of you two, Soli or Tommy, if you have any questions, you email me. I check my email regularly, and people in here you can just ask. So, the rest of class, we've got one little quiz, rising air, sinking air quiz, which I have right here, which is exactly like what I told you it would be like, except I think I put it in an email yesterday. There's this highlighted part down here that I just couldn't resist adding. I told you it'd be exactly like it. So if you end up missing parts that are highlighted here, I'll give you your points back. But I want you to try them. And then tomorrow we're going to have, oops, I deleted that window. The quiz over climate mapping. So the stuff you're doing your project on. And we've done 2 practice quizzes already. If I go back through here, climate mapping, this looks like that was practice. So class number 69, here's a practice quiz number 2. Somewhere before that we've got another practice quiz. Is it this one? I don't know. Oh wait, class 68. Yeah, so class number 68 and class number 69, those are 2 practice quizzes. And the quiz is going to be very much like those. And if any of you in here want me to make a copy a new copy of that so you can try it, I'd be happy to do that. The rest of the class is just